Next up is Blake Caldwell. Blake is from Oak Ridge National Laboratory. He's a system administrator there. He's part of the team responsible for maintaining, operating the Spider file system for Titan and other smaller Lustre file systems at ORNL. Blake Caldwell.
Hey everyone. So my name is Blake Caldwell from Oak Ridge National Lab. It's really exciting to see all the presentations here on just tuning and especially at the at the LND layer. So now it's just up to us to take all this knowledge that's being presented here and put it back into the community. So I mean, one way is like into the Lustre documentation or forums. It's up to us now to disseminate that information. So as I was going through this, preparing the slides and the tuning process itself, like it was difficult finding this information. I found myself going to Lustre or Google Groups to search through various incarnations of the Lustre Discuss mailing list, and also like having to go through the source code itself. So hopefully we can make it easier for others. So my presentation is going to be on the TCP LND and some tuning that we did on it to try to get the most out of a particular file system that it started out as a troubleshooting effort to figure out why we're getting terrible performance out of this system that should, is dual 10 gig bonded interfaces that we should be able to get good performance out of. But we were seeing 1 gigabyte per second, 1 gigabit per second. So just there's some advantages to SOC and LND. I'll talk about those, and then kind of overview of the system that we did the benchmarking on, the tuning on, and then some steps that we can take to go through verification and choosing appropriate tuning parameters. So SOC LND, it's not really getting the same amount of attention that the O2IB LND gets, especially at the large installations. And this was an example of one of our not our first foray into the TCP LND, but it was somewhat of a new experience for us. So, there's a kind of lack of information out there on it that we're trying to capture. So some advantages that is compatible with existing infrastructures. A lot of sites already have a LAN or WAN that's already implemented and vetted. They're happy with it, but it runs Ethernet. So if they can run Lustre over that same network, that saves a lot of effort. That you don't need to, revalidate the network, look at security policies again. You can just leverage that existing infrastructure and, run Lustre over it. So as a system administrator, the second one's really important to me, kind of a pipe dream. It'd be nice if all this was on one fabric, management Ethernet, IPMI, LNet, instead of having, 3, 4 different wires run into an OSS. If we can, use one, it would be a huge win. So that's currently possible with TCP. So it also gives you the ability to implement some security. So you can do access filtering using just conventional TCP IP firewalls. So something you can't really do with InfiniBand. You can specify exactly which clients you want to connect to your file system, and it's not very hard to do. You can do that, host-based firewalls or even like traditional firewalls on the router. So it also channel bonding is native in the Linux kernel, so it makes it really easy to do active-active bonding and get double the performance and also have that failover capability. So the system that I went through this tuning process on is a Lustre system that was deployed for the spallation neutron source at Oak Ridge National Laboratory. I won't talk a lot about the facility, but it's a really unique facility that we have at the lab. And so the file system itself is 448 terabytes with a DDN SFA 10K backend object storage. And so we verified that the backend storage is capable of 12 gigabytes per second with XCD. So we know that's not going to be our limitation. With the configuration with dual 10 gig bonded interfaces, we should be able to get 8 gigabytes per second out of the LNet layer. So about 1 gigabyte per second out of each 10 gig link, 2 per host, 4 OSSs. So that's kind of the target, where we'd like to get to. So I wish I could say we got there, but it's always, incremental progress is at least a step in the right direction. So one thing that complicates this is that it's actually over where clients are going to be about 1 to 2 miles away from where the file system is actually located. So we thought this might be, this is a non-trivial distance. There might be a little latency that we have to consider in these tuning parameters. So I'm going to discuss what we did with that. So this is a diagram just of kind of a simplified network infrastructure. And I mean, as you can see, there's a lot of links. There's a lot of things that can go wrong or possibly just not be tuned quite optimally. So it makes the tuning and troubleshooting process a little complicated. So the important point here is that to get full bandwidth from the Lustre clients to an OSS, we need to actually have 2 flows so that we'll use both links. So a single flow is going to be hashed over the 4-tuple of the source IP, source destination, destination IP, and destination port. If any one of those are different, then it will the hash will be different, and with optimal configuration, we should use all 2 links. So we observed that sometimes that wasn't always the case, that we'd have collisions where it would still be limited to 1 or to a 10 gigabit connection between the clients and the OSS. But in aggregate and in best case, we should see 20 gigabits. So separate from the arrows that are going up or down, the Lustre port or the port numbers there kind of show how this works with Lustre. That when you set up a TCP connection from the clients to the OSS, it's actually going to open up 3 ports, and so you're going to have different hashes for those connections. So one's going to be input, one's going to be output. So really, to take advantage of that, you need to be able to write to multiple OSSs. So first you have the basic network validation. You have layer 1, layer 2 validation. iPerf is just a reasonable tool it's a reasonable test just to verify that you're getting reasonable performance out of it. So you want to make sure that you're getting more than 1 gigabit per second out of it. If you can get 10 gigabits out of the links, then maybe we can move on to the next step of tuning. You can use iPerf with UDP to test for packet loss. Don't test at 10 gigabits per second because you're going to get packet loss at 10 gigabits, but try 9 gigabits, maybe even 8. And if you have 0% packet loss, you can move on. You're probably not going to have problems with the layer 1, layer 2 network. So this is complicated by having redundant links. We have more links to test, and testing any individual link means that we have to disable all the other links. So in the diagram previous, you can see that to test all the possible links, it's a very long and time-consuming process. So you can also check. It's important just to make sure you have a jumbo clean path. Send pings of about 9K from host to host. Make sure that those make it through. So we were interested in latency measurement. Was it a non-trivial latency increase by having a distance between of 1 or 2 miles? So you can use ping to do this. You can use netperf. I chose to use netpipe. I could understand a little bit more of what's going on, and it also gave me tests at different message sizes. So we're not actually testing the latency at the network layer. We're interested in how long it takes to go up to memory. More application level latency. So with netpipe, you can give it a -I option, which will invalidate the cache. So before the test, so you're doing a more accurate test of copying of a transfer between a buffer in main memory on one host to a buffer in main memory on the other host. So some of the measurements we got using close to 9K messages, so it would be encapsulated in one packet. We had 105 microseconds from ORNL to SNS. So it wasn't a lot more than just the latency we saw between 2 OSSs that were basically right next to each other. They were separated by 2 switches. So, we had some inter-switch latency there, but, it's kind of surprising. It's not a big difference. We're basically still talking data center latencies. What is interesting is that the difference between what, like a back-to-back connected OSS without going through a switch was much lower, that we would see about 40 microseconds from host to host if they were connected directly to each other. So maybe something for further tuning, further optimization, we might want to look at why that latency was higher between two OSSs. So, and just for comparison's sake, it gets down to about 20 microseconds for IP over IP connected hosts. So interrupt Kalessin is something that's important to consider. I won't really go through it here, but the Miracom Performance Tuning Guide is a really good resource to go for that. They just kind of explain some of the parameters on the Miracom cards and just give you some pointers to start there. So this ended up being the problem with our system. SACs were disabled, and just intuitively that that was a problem. It slipped by us several times at first because it's not something we were checking for. It's enabled by default with all Linux distributions that I know of. But what happened was we had InfiniBand packages installed on these nodes because they're InfiniBand connected to the backend storage. So we had all the OFED packages installed, and there's a script in there and /sbin, which sets all these tuning parameters, and it's optimized for a local area InfiniBand network, IP over IP, where you can expect in order and lossless, low latency connections. So all these parameters were not what we wanted at all for our system. So it's turned off ACKs because they just weren't important in that case. But for our case, when we had multiple router hops, out of order delivery was more of a problem. It turned out to have a really big effect. So another thing is we found a difference between some hosts that were connected, with identical configurations except for the actual hardware. Some hosts were getting about 600 megabytes per second. Others were getting 900 megabytes per second. We couldn't figure out the difference. And the difference was in hardware. One was the AMD system, the other was an Intel system. We found the AMD system, its chipset that we had, is the specific motherboard limited the max PCIe payload to 128 bytes. Miracom and Mellanox, they'll recommend that you go up to 256 bytes if possible. So that was the difference, that the hosts that were getting 900 megabytes per second with a single-threaded DD did have a max payload of 256. So just might be something to check. So some of the parameters, I won't go into details here, but they're specific to our environment and the kernel we were running. We were using 2618, so there's some potential bugs with using QBIC or even the BIC congestion control. So we decided to go to HTTP. And a lot of these are recommendations that we pulled from the fasterdata.es.net site. So it's another great resource for these parameters. So now getting into SOC LND stuff, your knob that you can tune with the SOC LND, credits and pure credits. There's enable IRQ infinity. That's something to look at. We didn't need to mess with that for our situation. But briefly, to get a little information, what we can do from LCTL, we can do a con list, and it'll show us all the connections that Lustre establishes. Like before I did this con list command, I did a single DD from one client to the OSS. So there's a write, there's a couple gigabytes from the client to that OSS4 there. And so we have the port numbers there, and the very right-hand side of the screen there we have the TX and RX buffer sizes. So by default, they're the same as what the Linux kernel is going to see, or what we set the Linux kernel to auto-tune the TCP buffers at. So by default, it should be 65536 and then 87380. So that middle connection there, the I stands for bulk in. We're not doing any input on that connection, so it's still using the default RX TX buffers. Now for the bulk out, it's scaled up the TX buffer a little bit because we've run the test already. So the kernel auto tuning has already taken effect, and it's scaled up the TX buffer there, and we'll see that effect mirrored if we do a con list on the OSS, where it scaled the receive buffer on the input bulk end channel to the max, which is 16 megs. So this is just something you can kind of check to verify that it's doing what you want as far as auto-tuning the TX-RX buffer sizes. You'll notice in the Lustre documentation, if you look at these parameters, it'll say danger, don't touch. But it's actually doing a reasonable thing, so it's just following the kernel auto-tuning, which we have enough confidence in. So some of the Lustre parameters, we turned off checksums for these because we noticed a huge throughput increase. Going from about 400, 600 with the checksum turned on, we'd go up to 900 megabytes per second without. So we're just relying on TCP doing its TCP checksums and not relying on the Lustre level. Something else, max RPCs in flight. This was discussed in an earlier presentation, whereas it's a really useful tunable. It's more at the Lustre level. It's not really an LNet tunable or parameter, but you can use it to kind of counteract some problematic behavior that you'll get with TCP. So we noticed with an IOR run from several clients writing to even the whole file system, but if you just take one OSS, we had congestion on the one link or two links from that OSS to its switches because all the clients were writing to it. So on those links, we had TCP congestion control kicking in. And we noticed as soon as that happens, throughput would drop maybe by half. And we could actually get better throughput if we limited max RPCs in flight to something, actually 1 was adequate. But if we, dropped it from 8 to 4, something lower, we'd get better throughput because it would preempt TCP congestion control. So this isn't an ideal solution, but it kind of points the finger at where the problem is. In the future, we might want to look at different congestion control algorithms. So another reason you might want to tune this is if you have a really long, fast network path, so where you have a high bandwidth delay product. In our case, this was not at all the issue. So at the bottom, there's the bandwidth delay calculation for our network. 275 kilobytes, a 1 megabyte RPC is easily going to saturate the network bandwidth. So it actually doesn't make sense with just 1 RPC. But if you had a long path and you had 10, 20 megabytes that could be in flight, you would want to tune up the max RPCs in flight. So some things you can do with LNet self-test. First you want to try just concurrency 1. With distribute 1-to-1, so just one client to one server. And if you throw in some concurrency there, you should see about 1150 megabytes per second out of that one connection. So that's pretty good. That's about our 1 gigabyte per second out of that link. Now, if we use distribute 1-to-4, we're going to have one client talking to 4 servers, 4 OSSs. So then we're going to start to see the effects of hashing. So that's how you evaluate the effects there. And then we also might be interested in examining the TCP congestion control aspect more. And for that case, we'd do a distributed 4-to-1. So we'd be overloading that server. Something else that would be useful, we didn't get time to do this, is look at a packet capture of once you run LNet self-test, look at a packet capture and look where you have dead time, where either TCP is ramping up or event where you have after you have a packet loss event. How long does it take to ramp up the congestion window or the receive window back up to 16 megabytes in our case? So it might point the finger at other places for optimization. So I want to get to this example of of changing the credit sizes and get to see its effects. So at the top there, we're just running with concurrency 1 on LNet self-test, just with concurrency 1 and then 1 megabyte IOs. And we're not saturating the link. We're getting about 700 megabytes per second. So just one RPC, one test going at a time, that's reasonable. If we ramp up the concurrency to 8 or even 16, then we start to fully utilize that link. So there we get almost 1,200 megabytes per second out of it. That's as much as we're going to see out of that one connection. But But what's interesting with concurrency 16 and pure credits and also just credits at the SOC LND layer set to 8, it's not going to allow all those tests to send messages on the wire. It's going to start queuing them up. So we can see that in the TX credits there, or the TX queue of -6. So there's the negative number means there's 6 messages there that are queued waiting to be sent out the wire. So if you see that number ramping up, getting really high into the hundreds, that could be your problem there. So it's an indication that you want to start tuning credits and also pure credits. So we're done on credits versus pure credits. Pure credits is just between peers, so it's more of a fairness control rather than flow control. That by lowering pure credits, you can control how many messages you're going to allow between 2 NIDs, rather than credits is going to be aggregate across everything. So another test that I thought would be interesting, just to demonstrate the pure credits versus credits differential, is set credits to 4, but pure credits at 2, and then run a test from a single client to that server with concurrency equal 3. So we can see it's expected behavior that if you look at under proc, if you look at the NIS file, you can see like the queue states of that peer. But in the peers file, we can see that there's one message being queued, and it's exactly what we'd expect. That it's limiting the credits or the messages that can be on the wire to 2, and that third message, part of that third test, is getting queued. So some of the results that we got to with our bonded 10 gig interfaces were 2.1 gigabyte sequential writes using FIO. We weren't able to get more with DD. We had to move to an application that was multi-threaded and getting writing separate files. So that's more of a Lustre limitation that we needed to get past that single-threaded, single-client performance. But that was how we got full utilization out of our links. Something else that was interesting is that we were able to get pretty good throughput with a file copy. There's a really neat utility out there, MCP from NASA Ames, where it does a multi-threaded copy. So with some of those options, we could get really respectable performance hashing across both bonds, doing a file copy. So this is just cache disk, but you can do the same thing between 2 Lustre file systems. And then just with DD, it wasn't a great test, but everyone's familiar with it, and it's where we started. So we were able to get 900 megabytes per second with the parameters that I went through previously in the slides. And importantly, that was with the max payload 256. We saw much less with 128. So in conclusion, that's it. Is there anybody with questions?
I think we've got time for about one.
I'm sorry, I didn't catch which version of Lustre this was.
That's
1.8?
important. It was, 1.8. Thanks.
Yeah, because I've done some tests in the lab, and I noticed the checksums difference, turning it off pays off a lot, but I hadn't noticed any big significant effect in 2.x.
Okay. I understand that there's improvements in 2.x.
I wonder whether you you measured the improvement in having the channel bonding inside the kernel rather than just using the standard multipath provided as an external module. And the second question is whether you consider any kind of side effect of modifying this checksum for Lustre for the whole working of the machine. I mean, for other purposes, whether there are side effects.
Mm-hmm. So the first question, I actually comparing channel bonding in the Linux kernel versus something else.
Right. Because we do have channel bonding, but it's not inside the kernel. It's just the multipath that is provided by external module. I mean, the module to multipath to NIC with the 10 gigabit Ethernet.
Okay. So for this particular deployment, we wanted to go with a very stock Lustre kernel, or stock distribution, and we wanted to stay with 1.8, the 1.8 branch. So I mean, using the kernel channel bonding was the only way I knew to go about actually getting the bonded interfaces. So, and then your second question about side effects, and we determined that there's going to be TCP connections or TCP checksums between at each point of the link, and then that's going to be adequate for us. We weren't looking for an end-to-end checksum at the Lustre level.
Blake Caldwell, ladies and gentlemen. Thank you.